essence of the scientific method is the willingness to admit you're wrong, the willingness to abandon ideas that don't work.
The world always needs heretics to challenge the prevailing orthodoxy. We're lucky that we can be heretics today without being burned at the stake.
What I'm trying to argue for is to think about things from a new point of view.
The question is time real? Does time have any objective reality? And of course it does.
That to know when you know and when you don't know, and what it is you know and what it is you don't know, you got to be very careful not to confuse yourself.
My sense is that the scientific way of thinking, questioning, some delicate mix of creative encouragement of new ideas and the most rigorous and skeptical scrutiny of new and old ideas, I think that is the path to the future, not just for science.
I can do a circle in space. But if time and space are really together as part of a four-dimensional universe, why can't I do a circle in time?
We should only talk about things that we can measure. Try to define things in terms of only things we measure. Let's formulate the equation mathematically, or let's guess the equation, or all these things are tried all the time. That's very useful, but we all know that. That's what we learned in the physics classes, how to do that. But the new problem, where we're stuck because all those methods don't work. If any of those methods would have worked, we would have gone through there.
Have to be willing to challenge because we are in desperate need of change.
You could create a geometry where you could do a circle in time.
So when we get stuck in a certain place, it's a place where history will not repeat herself. And that's makes it even more exciting, because whatever we're going to look at the other, the method and the trick and the way it's going to look is going to be very different than anything that we've seen before, because we've used all the methods from before.
I'm going to add this to my playlist.
We've been exploring the idea of three-dimensional time. Three-dimensional time by no means is a new idea.
Channel, you should check
I have
it
to
out.
ask, was there ever an idea that had more than one time dimension?
Yes, absolutely. So, Nth Barr was one of the people at USC who's pioneered this possibility. He has studied theories with two time dimensions. They're much harder to make work. I mean, if you have trouble thinking about extra dimensions of space,
look
try
at
to
all
think
those
about extra
playlists,
dimensions of time.
Yet, three-dimensional time can be derived by using a set of new and peculiar equations. Let's suspend everything we know about time for a moment and use our imagination, if you will. Let's allow time to be a two-dimensional vector running in the direction of the arrow of time. We can assign this t1 coordinate to periods of time, and we can assign this t2 coordinate to present moments of time. If we allow the arrow of time to slide more towards the periods of time coordinate,
time moves by faster with more periods for present moments.
Or, if we move the arrow of time more towards the present moment coordinate,
we get more present moments per periods of time.
If we move the arrow of time so that it runs perfectly parallel with the periods of time coordinate, we end up with the past, present, future within a single moment. Or, if we run the arrow of time so that it runs perfectly parallel with the present time coordinate, we end up with an ever-present moment in a single period of time. The concepts of ordinary time and time dilation found in physics have equivalences in three-dimensional time which can easily be accounted for. Temporal events that happen on this side of the arrow of time correspond with the Lorentz transformation, where temporal events on this side of the arrow of time correspond with the inverse Lorentz transformation. These definitions give rise to temporal mechanics that, when applied to mass and energy, maintain conventional conservation laws.
What does it mean to talk about the origin of mass? In Newtonian mechanics, it really wouldn't mean anything at all. I teach students the three laws of motion, Newton's three laws, but before that, we discussed the zeroth law. And the zeroth law of mechanics...
Wow, this is actually really good.
...is that mass is conserved. that mass doesn't change.
Hey man, I'm too underground to actually release an album.
Mechanics and was the great achievement of Descartes,
Yo, I'm not on fucking Spotify.
and Newton to realize.
You think they fucking sue me if I like release this shit? This shit's they fucking sue me. The time space fucking police will sue my ass. No, I'm just joking. I might actually like. I think I'm just gonna like let it play out.
The central equation of classical mechanics, F equals
I made a music
ma,
video.
which relates on the left-hand side of the dynamical concept of force to their motion through space and time, their kinematic quantity of acceleration. And to relate those two, you need some kind of conversion factor, and that's the role that mass plays. Something that didn't have mass, something that could give an origin to mass, wouldn't know which way to move. It would be a senseless object. Mass was a primary concept that couldn't be reduced to anything else. This all changed
I've never really used low-pass
at the
gates that
beginning
much
of
in
the
my
20th
life.
century when Einstein introduced his second law. It's called the second law because there's a familiar first law, E equals mc squared. This way of writing Einstein's law of the conversion of mass into energy suggests that perhaps it's possible to explain mass in terms of a different thing that could be primary, that is energy. And in fact, Einstein's original paper on the subject has this form of the equation.
The point particle mass has no spatial extension. Neither does the center of mass reference frame. For any object, regardless of size or shape, it has no spatial extension. We can treat mass as a negative volume of time, where t squared represents linear time with a one-to-one
So the secret to my sound?
between periods and present moments, and minus t prime represents the negative passage of time. We can multiply in a variable n to increase or decrease the relative density, or periods per present moments. A displacement in the passage of time would indicate acceleration. The fundamental equation of Newtonian physics, F equals ma, can be substituted with these relationships between temporal coordinates, giving rise to temporal mechanics. The temporal mechanical definitions for mass and energy are consistent with relativity. Applying them to the magnitude of some net force with a primary and secondary state, and applying
that's
the
what they're actually supposed to sound
Pythagorean theorem, can be used to derive the inverse Lorentz function.
I like the other version though too, but we gotta progress it along into the
primary state is the initial condition
lives.
prior to acceleration. The linear time to passage of time variables have an inversely proportional relationship that can be set equal to 1. Since the acceleration term corresponds to a ratio between spatial and temporal coordinates, this becomes the expression for the primary state. In the secondary state, the linear time variables between the mass and acceleration terms are set equal. Since the linear time to passage of time variables have an inversely proportional relationship, the passage of time variable is proportional to the inverse spatial coordinate. Therefore, the secondary state represents to where and when the mass has been accelerated. Subtracting the primary state from the secondary state, we derive an equation in the same form as the reciprocal Lorentz factor, alpha, with the exception of units. Applying the right units
I went to this show tonight, and they were playing like tech house, bass house. I was like, yeah, this is good. And I told my friend who I've been making music with for like 7 years, I was like, man, this techno sounds nothing like my techno. My techno sounds way different.
Much more dynamical, yet it still maintains Lorentz invariance.
More generally, in our theories of physics and the standard model, we understand things much, much better if masses are zero. And mass is somewhat of an embarrassment.
When mass is treated as a temporal scalar, the ratio between t1 and t2, or the slope of periods per present moments, can be skewed to account for time dilation, setting t squared equal to 1, using a reciprocal relationship between t1 and t2. This allows the rate of
Especially if you
periods
gave me a
per
bunch of
present
ketamine.
moments to change relative to Lorentz transformations and relativistic motion without affecting the passage coordinate. In this way, inertial mass can remain unchanged or Lorentz invariant, whereas momentum can undergo relativistic changes, increasing or decreasing. Mass can be treated as a three-dimensional time scalar within a four-vector metric. The temporally oriented four-vector does not replace the standard four-vector. Rather, these two metrics work together, consistent with standard notation and theoretical arguments. The temporal four-vector is supplemental to contemporary physics, not oppositional.
I can do a circle in space, right? But if time and space are really together as part of a four-dimensional universe, why can't I do a circle in time?
Temporal loops can cycle orthogonally in relation to the direction of the arrow of time. Though the passage of time coordinate and present time coordinate may reverse through half the cycle, linear time passes from the past through the present and into the future without change. Together, they form a dynamical relationship consistent with time-dependent phenomena in quantum mechanics, such as quantum electrodynamics. This temporal loop model is also consistent with the relationship between confinement and asymptotic freedom in quantum chromodynamics.
We should own up to the approximations being made. It's not quite true that the up and down quarks are massless. In order to account for some of the details of the patterns of masses, in particular technically for the mass of pi mesons, it's necessary to put in some finite value for the up and down quark masses. But it turns out that the finite values we need are only about 1% of the mass of the proton and neutron. So really, this is the origin of mass. Starting with QCD light, where there was literally no mass, we get 90% of the mass of the proton and neutron. But that answer may not give you a warm and fuzzy feeling. One would like to understand in a more comprehensible way that would give some satisfaction from this marvelous result, where that mass came from.
The temporal definition of mass is very handy in cosmology. The temporal loop model can be extended into modern cosmology in several
Holy shit, I'm
ways,
still recording this?
accounting for some of cosmology's unanswered questions.
Caltech professor Fritz Zwicky looked up to the neighboring Coma cluster of galaxies and observed something strange.
You could estimate the size and then obtain the mass in the cluster, and he found that it was vastly more massive than accounted for by the luminous matter.
Something didn't add up. The galaxies were moving too fast within the cluster for the amount of illuminated stuff he could see.
The subject remained dormant till Vera Rubin and Kent Ford measured galactic rotation curve.
Like Zwicky, her observations also seemed strange.
The only way to resolve this paradox of galaxies which spin 10 times too fast is to assume that there is a halo of invisible matter surrounding the galaxy, keeping the galaxy whole.
If this is a galaxy viewed edge-on, and you measure the velocity of gas going around the galaxy,
the gravitational acceleration due to a mass at the center would be m times g divided by the radius squared to the star, and that has to equal the acceleration, and the acceleration is the velocity squared divided by the radius. So this would then say that the velocity falls off like 1 over r. This is Kepler's planetary law. It's usually expressed in terms of the period rather than the velocity. Velocity falls off 1 over r with host computer. That's not what was seen by Oort, and it's not what's seen by anybody since.
We believe in the feedback loop.
Velocity is pretty much constant. Not the angular velocity, incidentally. It's not like this thing is rotating like a big giant pinwheel, but the linear velocity appears to be constant. So instead of saying all the mass is at the center, let's say the mass is distributed, and let's introduce a function m of r. M of r is the amount of mass contained within a sphere out to radius r. Not of a constant mass at the center, but of varying mass which varies like m of r. And in that case, v is constant, doesn't change with distance, and therefore we find that m of r must grow like r. M of r increases as you move away from the center, and so as you move out, this is not the mass density, incidentally. This is the total mass within a radius r.
Why doesn't anyone make techno like this anymore?
Out to the outer boundaries of a galaxy, and even beyond that. At the moment, it looks like a piece of luck that the velocity curve is flat. And I don't know a good, substantial, simple argument about why that's the case.
Three-dimensional time can be used to account for the anomalous rotation curves of galaxies without appealing to the presence of dark matter. The expression used in Susskind's example, where mass is a function of the radius, could be used in an alternative way to mathematically argue that there is an increase in the passage of time as the radius increases. For simplicity, we can substitute the basic temporal definition for mass with m, letting the variable n equal 1 for simplicity. Since we are dealing with a change in the passage of time relative to a gravitational field, as opposed to dealing with some mass, we can drop the minus sign. Since the t squared term is proportional with the units for g and v squared, only the passage of time term can vary. Therefore, the passage of time can be a function of the radius such that the passage of time increases with the radius consistent with Einstein's equivalence principle. This tells us that the relationship between inertial mass and gravitational fields can remain consistent, while the radius as a function of t prime varies with the distance from the center.
Dark matter's invisible presence is everywhere, or so it seems.
Here, I'm going to tell you exactly, or show you exactly what you should spit. You should sing this right here.
Exist. There are many suspects, but no answers.
This paragraph right here is what you're
observing something you can't see.
Because I'm on the essence.
Dark matter has yet to be detected. We haven't detected an actual dark matter.
Exactly. Read it.
It has two very important characteristics. The first is that it does not interact with light, so it does not emit and it does not
It would
absorb
have been
light.
perfect. I could have sampled that, made a vaporwave track, but whatever.
So, how do we study dark matter? Well, one of the primary mechanisms we have for studying it is through its gravitational effect.
If you scan the sky with a powerful telescope, you'll discover that in certain directions, the image is distorted. It's as if you're looking through a very big droplet of water.
Basically, the idea behind gravitational lensing is that you're looking at the light traveling towards us from a distant source. So, in my analogy, the candle is a distant galaxy, and I'm an astronomer on Earth looking at this distant galaxy through my telescope. And in between us, there's a giant clump of dark matter. A wine glass can be an optical lens. And as I look towards this distant galaxy here, we see features like rings and arcs instead because the light has been deviated through the lens.
She's not actually drinking?
Just a little illustration to get you to
I'm so offended. She's not actually
here,
drinking wine. Will you take my advice this time?
Galaxies are distorted in this spherical pattern. We see a ring and we see arcs, and all these shapes are distorted.
The explanation is that gravity bends light. And this is a nice picture of the concept. Gravity is bending light. The images you see get distorted. The problem is, or the remarkable discovery is, that the light is getting bent even where there's little or no visible matter. No presently known form of matter fits the bill for this other stuff. It might be better to refer to the cosmological dark matter problem as an excess acceleration problem.
Dark matter is an unfortunate name. The name sort of sounds like mystery mongering and sounds like a cover-up somehow. If we just talked about excess acceleration, which would be more accurate. What's actually observed is that things like stars and galaxies don't move the way they should according to the laws of gravity. There's some extra acceleration, as if there's more stuff. that's exerting gravitational forces.
We have already examined how three-dimensional time can be applied to acceleration. Acceleration involves a temporal displacement, lessening the rate of the passage of time as the object begins to transversely move through space. Deceleration involves a spatial displacement, lessening the rate of the change through space, followed by an iteration of repeating diminishing lengths of space as the frame of reference concludes transversely passing at an increasing rate of the passage of time.
This is one of the most famous results from gravitational lensing concerning evidence for dark matter. This is called the bullet cluster. A cluster of galaxies contains two visible components. It contains galaxies and it contains hot gas. The hot gas is actually a lot more massive than the galaxies are. It's actually two clusters of galaxies that have collided through each other. When we look at the different components, these are the galaxies, we basically see that the galaxies have passed through each other during the collision. However, when we study this system through gravitational lensing, we can demonstrate that most of the mass is located at these blue peaks here. We learn two things from this. One, there's a lot of mass that is unseen, we don't see. And secondly, it doesn't interact with normal matter. Had it interacted with normal matter, it would have stopped and been slowed down here. We can compare the location of the stars and the galaxies and this hot gas that emits an X-rays, and we find that all the normal matter is located within the dark matter scaffold. Normal matter is confined to lie within the gravitational potential levels that are defined by the dark matter.
If we apply the new equivalence principle to dark matter and dark energy, it becomes apparent that when we look at extremely distant objects, or when we look at extremely massive objects, such as galaxies, we're not only looking at three dimensions of space, we are also seeing three-dimensional time. What about gravitational lensing, or dark matter halos?
How do you find something that is invisible in space?
Just as a lens bends light, a large mass in outer space, such as a cluster of galaxies, bends light traveling near it. This is known as gravitational lensing.
So the secret to my
bending
sound
affects the light reaching us,
is that I
distorting
accidentally
images of whatever
put the
lies
clock
beyond the mass.
into the source of the
Light
mass.
Gravitational lensing detected dark matter concentrated in the halos of galaxies.
Looking at the distortion of light as it goes through galaxies.
And that's why you exist, the feedback loop.
Of dark matter.
When people found dark matter, everybody wanted to know what is it, you know.
If time is really three-dimensional, from our observations of distant objects in space, then we really do need to take it into consideration. Using the temporal 4 vector, we can see that there's one space component for 3 temporal coordinates. Recall what each temporal component corresponds with and how they relate to the temporal definition for mass. As t squared, or linear time, extends, both the period and present time components extend such that for any given moment, the slope between periods and present moments is 1. In this case, both the passage component and the mass are unchanged. The net effect of this is that the mass can be set over a single spatial coordinate for an extended period of time, such as a point particle mass. If we extend that spatial coordinate into being a vector of three-dimensional space, then that point particle mass can be spread homogeneously over some volume of space as well. In an odd way,
Even the feedback loop.
is in more than one place at the same time, even though that same mass is in the same place at more than one time. If we examine certain images taken as gravitational lensing,
Say what you feel.
familiar geometry comes to mind.
It's just in the halls of eternity.
Yeah, well, what
I went
is
to
42?
this show tonight. And they were playing like tech house. So I was like, yeah, this is good. And I told my friend who I've been making music with for like 7 years, I was like, Man, this techno sounds nothing like my techno. My techno sounds way different.
That contributes the extra gravity you need to keep satellite travelling at the right speed to keep happening. So the distance between the Earth and the Sun is about 150 million kilometres, and this L2 point is 1.5 million kilometres. But it's sort of 4 times further than the Moon is from the Earth. Okay, so we've got L4 and L5. Now, they're the sort of slightly too subtle ones. So if you look at L4, so this is the one that's sort of ahead of the Earth. So the Earth's coming around this way. This stays permanently ahead of the Earth. And just the same for the L5 point over here. So it's pulled towards exactly this point. And if you think about Jupiter and the Sun as your two bodies, then actually there are a whole bunch of objects which are kind of trapped at the L4 and the L5 points. They're called Greek and Trojan asteroids. Generically, they're called Trojan asteroids. They don't actually collect at L1, L2 and L3 because it turns out those orbits are actually unstable, whereas L4 and L5 are actually stable points, which means that when stuff is there, it stays there. A little perturbation, it won't actually move away from the L4 or L5 point. So any pair of objects where in the region where those two objects are sort of the dominant source of gravity, you can find these Lagrange points and these kind of trapping effects.
Strangely, there is a geometrical overlap between the location of Lagrange points and the distortion of an image by a galactic dark matter halo.
Images from the Hubble Space Telescope show a distant galaxy framed by 4 images of the same supernova, a kind of mirage that's been dubbed an Einstein cross. It's called gravitational lensing, and it's a common trick of the light that shows up in tons of deep space images. In this case, light from a distant supernova was warped on its way to Earth when it passed through a galaxy cluster, splitting the image into 4. It's been observed a few times with things like this quasar, but a Johns Hopkins University astronomer says this is the first supernova.
It is really quite remarkable that the first multibeam supernova was not a double or a triple, but an Einstein cross.
Space-time appears to act like a Bose-Einstein condensate, or a Beck, a superfluid where quantum entanglement occurs over long ranges.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. Each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that. If you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. This little wave packet over here can't tell whether it's this one or that one or that one. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system.
A Beck could allow the temporal 4-vector and spatial 4-vector to spread out homogeneously over more than one place at the same time, while in the same place at more than one time. A sort of temporal blob.
Well, it's kind of like a mass that keeps getting bigger and bigger.
More towards the center of a galaxy, relative to the gravitational field, there is a significantly lower rate of the passage of time. The rate of the passage of time relative to the Beck is at a higher rate than the rate of the passage of time relative to the galactic center, even though the Beck is cooler. Relative to the periods per present moments, the Beck is operating near the infinite momentum frame, primarily in the passage per present plane. This is analogous to a zero viscosity flow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
The propagation of gravitational waves should affect this Beck, creating a disturbance, sort of a billowing effect, similar to Lagrange points, but rather than points, blobs.
The blob. It's indescribable. Nothing can stop it.
These are just simplified examples of how three-dimensional time and the existence equations can be applied to the concepts of dark matter without introducing any new exotic particles. If we extend our temporal model out further and let the energy density of the vacuum correspond with a very high rate of the passage of time, since it is associated with infinitesimal mass, it can be associated with the infinite momentum frame. Therefore, it's reasonable to extend our model.
The dream that she dreamt about, she said.
The observations of dark energy.
Like deja vu.
A few years ago, astronomers decided to use redshift.
So you should probably take my advice then, right?
Expansion history.
And read the brainstorm, or let me read it.
I'm feeling it.
I'm feeling really inspired. Like I'll read it. I'll read it. And I'll ad-lib it. You know, Rick and Morty was made like some dude.
Tell you how much the universe has stretched. So that means that by the time it reaches us, it looks red. That's called redshift. And exactly how red it looks tells you how much the universe has stretched since the time of that.
Give me the book and I'll tell you.
You can map out for
your inner soul.
Supernova telling you how far back in time it exploded, and you can find out how much the universe has stretched since that time.
Why did I point that specific
some of the largest
page out?
telescopes in the world to do this over a number of years. 10 years later, we actually had enough supernovas to do this measurement, and there were just a few options. One was that the universe was going to be slowing because all the gravity in the universe would slow the expansion, and option 2 was a little bit more dramatic. That was one where the universe slows to a halt, and then collapses in a big crunch, and the answer turned out to be none of the above. We seem to be faced with some new component of the universe that we hadn't recognized before. Apparently the universe is dominated by perhaps a dark energy, which would be some energy spread through all of space that we've never identified previously. We still don't know what it would be, and that it could be perhaps powering the expansion of the universe to be speeding up. That's one possibility. Another possibility is maybe even more bizarre. It's possible that Einstein's theory of general relativity needs modification.
However, if we're going to use three-dimensional time to account for dark matter and dark energy, we're eventually going to have to face the big question. What about the Big Bang? How does three-dimensional time affect our observations of the Big Bang? Since the present time coordinate is not dependent on the periods of time coordinate, the concept of a beginning of time doesn't really make much sense. The conceptual point of origin, where space and time appear to have begun, is known as the Big Bang singularity. Here, space-time is reduced to a single point. On the other hand, when viewed through the lens of three-dimensional time, it becomes nothing more than a temporal vanishing point. It can be argued
this is actually really good.
Cosmology is a collection of artifacts resulting from limiting time to a single dimension.
Hey man, I'm too underground to actually release an album.
The idea of a beginning
I'm not on fucking Spotify.
is nothing much more than a temporal vanishing point.
My name is Fred Hoyle. I am the inventor of the well-known words Big Bang.
I might actually
to refer
I think I'm just gonna let it play out for a while.
But I'm afraid
I don't
I
made a music video.
really believe in
I'll
the
send
Big
you the
Bang.
link.
I'm generally speaking not a believer in popular theories.
So what are the mathematical
do you want to see my music video?
Big Bang Theory anyway?
Does anyone want to see my music video?
Explanation for why we see a redshift in distant light as we look
do you want to see my music video?
outer space at more distant galaxies.
Does anyone want to see my music video?
Galaxies are moving away from one another, indicating that the
do you want to see my music video?
On the other hand, what if light itself becomes red?
Does anyone want to see my music video?
Greater distances through space, or due to some kind of...
do you want to see this universe I created?
If we lived in an infinite, unchanging universe, the entire sky would be as bright as the sun. but the sky is dark at night, both because the universe had a beginning so there aren't stars in every direction, and more importantly, because the light from super distant stars, and the even more distant cosmic background radiation, gets redshifted away from the visible spectrum by the expansion of the universe. So we just plain can't see it.
On the other hand, couldn't it be the case that light redshifts on its own after having traveled for vast periods of time? As an alternative to the Doppler effect, three-dimensional time can be applied to frequency, wavelength, and the speed of light, and successfully account for cosmological redshift. Let's examine a moment of undisturbed travel of a single photon. The difference between the final mass and the initial mass of the photon equals 0. There is no change in energy or momentum of the photon as it travels, undisturbed for a period of time. So that the mass of the photon doesn't change in order to maintain the conservation of energy, the passage of time must decrease proportionally as the period of time increases. Since there is a change in the period of time for a single photon, the passage of time decreases relative to the observed frequency of the traveling photon, and the photon appears to have increased wavelength. The period of time for a traveling photon increases proportionally with distance. Since the passage of time decreases as the photon travels through space-time, the wavelength of the photon becomes longer relative to some observer in a non-relativistic frame of reference, say that of an astronomer billions of light years away. Well, what about the expanding universe?
Now, it was Hubble in the late 1920s who made the observations of the night sky, which led us to see that our universe is expanding. So imagine a point so far out there that the average recession velocity is the speed of light. So that would form a sphere, which we call the Hubble sphere. The observable universe is larger than our Hubble sphere. It's actually limited by what's called the particle horizon. The observable universe has a radius of over 46 billion light years. The diameter is about 93 billion light years. And 13.8 billion years ago, everything in that volume and everything beyond it that we can't see would have been compressed into a tiny, infinitesimally small point that we call the singularity.
We can reinterpret the scale factor in the cosmological equation of state, the Friedmann equation, and apply it to 3 dimensions of time rather than 3 dimensions of space. We get a range of different rates of the passage of time over various periods of time per present moments spanning the history of the universe.
The basic question that we want to answer in cosmology is, what is the history of the universe? It really boils down to what is the time history of the scale factor.
Time plays a major role in cosmology and arguably is its most central concept.
The Friedmann equation says that A dot over A squared is equal to 8 pi g over 3 times rho plus maybe 1 over A squared or something. But it always comes in 8 pi g over 3. Lambda was introduced to get rid of this nasty 8 pi g over 3. It's called the cosmological constant. It was introduced by Einstein. It's also the thing which the newspapers call dark energy. There are basically 3 components to the energy density on the right-hand side. Let's call this matter, rho matter. It's just the mass within that region. I guess I called it M at one point, the mass within the region, divided by the volume. Rho, let's call it radiation. Energy density in radiation, instead of being 1 over A cubed, is some constant divided by A to the 4th power. All right, there is a third component of energy, what I'll call rho naught, and that's vacuum energy, dark energy, cosmological constant, all the same thing. And what I will tell you about it is it doesn't depend on A at all. It's energy that's there in the vacuum. It's the component which does not go to 0 as A gets bigger. In fact, you can think of it as a constant of nature. It's a number. It's there in the vacuum. I'm just going to write rho naught equals rho naught. It doesn't change. And it's A is equal to E to the square root of 8 pi g rho naught 3, I'm not going to write it, times T, exponentially increasing. Now with a little bit of work, you should be able to tell me how A depends on time for a given W. And you can find out how the universe expands for any value of W. With one exception. What's the exception? W equals minus 1, we'll see why, is exactly this vacuum energy here. If W equals minus 1, that says that the energy density doesn't depend on A at all. 1 plus W in that case would be 0, and we would just have C divided by A to the 0, and A to the 0 is just doesn't depend on A.
The scale factor for each component of the energy density of the universe can be substituted with a temporal scalar. This underpins the expansion of space as the explanation for cosmic redshift, conceptually replaced with the expansion of time. Notice that the scale factor for the matter density component is cubed. Since we are treating mass as a three-dimensional temporal scalar,
I'm going to tell the people the secrets of the
secrets
of this universe are like kind of
scalar. Furthermore, the scale factor for the
in the video.
Can be reinterpreted.
Check my latest 9-hour live stream
correspondence between
for the answers
moments
to the universe. Kind of.
Finally, the scale factor for the radiation component, raised to the 4th power, comes from the Stefan-Boltzmann law expressing the scale factor as a function of temperature. There is an inversely proportional relationship between the passage of time and linear time relative to inertial mass and relativistic momentum. This is easier to understand when examining the expressions of thermodynamics and how they relate to temporal mechanics. In a closed-loop thermal system, such as an idealized heat engine, the inversely proportional relationship between temperature and the change in entropy can be used to set the heat engine into motion. Substituting the passage of time for temperature and substituting linear time for changes in entropy, the thermodynamic expressions for a Carnot heat engine can be used as a mechanism for
the thermodynamic expression.
Now think about this equation today, at the present time. How much of adding up to the right-hand side comes from radiation? How much comes from matter? How much comes from dark energy, lambda? And how much is left over in this curvature term? The ratios depend on time because they scale differently. But the ratios today are called omega. The ratios are omega R, omega M, omega lambda, plus omega curvature. In other words, the omegas are the fraction of h squared today contained in each one of these terms.
If we apply the scale factor to temporal dimensions, the exponential growth of time intervals applies to either 1, an increasing proportion of periods per present moments, or 2, an increased rate of the passage of time. The first corresponds with massive particle propagation, and the second corresponds with inertial mass and momentum. Changes in the passage.
Yo, I'm gonna promote myself. I'm gonna be like, I make the worst music in Las Vegas.
And vice versa.
So, a model, then, again, a model...
You thought these Las Vegas DJs are bad? Check out my shit.
But you don't measure them completely. Some of them you measure, some you don't measure. But you just feed them in, grind the wheels, calculate AST. You're juggling various things. But once you have a model of 50 pieces, okay, then you have an A as a function of time.
Give me a bad rating. No, forget it.
I didn't get them. Trial and error. Trial and error. This one is not important. Everybody knows this is not important because you measure it directly. It just won't matter. Some of them, look, This one here is more or less measurable directly. Why? You can measure.
Wow, I probably shouldn't have posted that on Facebook.
And you can measure the dark matter and the luminous matter together. Basically, omega m is the ratio of this factor of this one. So that actually is measurable. We're going to talk about dark matter. Including the dark matter, omega m is about 0.3. These two are the ones which are not known. But what is known, at least in theory, is that this plus this plus this has to equal 1. This one is known. Therefore, this one follows. But you want to do better than that. Really what you want to do is, you really want to do better than that. You just don't want to say, well, this is 0.3. This one's not really known. Nobody's ever made it.
I will accept that award that no one gave anyone. You're the worst DJ, music producer in Las Vegas. Man, there's no one's gonna give that award out, right? I'm gonna make that shit myself. Yo, what the fuck are you talking about? I think I lost. He's like, I think I'm actually getting somewhere with this. Did you hear that? Alright, listen to my shitty music. Fuck these guys. went to this show tonight, and they were playing like tech house, bass house. I was like, yeah, this is good. And I told my friend who I've been making music with for like 7 years, I was like, man, this techno sounds nothing like my techno. My techno sounds way different. I could dance to this shit. Especially if you gave me a bunch of ketamine. You gotta appreciate the silence, man. The space between the space of the research. It's the notes that you don't play, man. Can you hear that I didn't? It's like the ambient of wherever you're listening it. Space between space research. Yo. I love how I'm not using a filter. I'm using 2 low-pass gates, no filters. I'm using a comb delay. I thought it was a comb filter, but it's actually a feedback loop. Comb. I could throw that serum effect, the filter on serum, but yeah, fuck serum. We're complex proing it. Holy shit, I'm still recording this? I didn't know I was recording this. Well, here's a huge ass file I'm never gonna fucking use. Hey, shut the fuck up. I'm gonna use this shit right now, you stupid bitch. Yo, it's SpaceyBlurr, the worst DJ in the fucking world. The worst in the fucking state. The worst in the fucking city. Las Vegas. Low bar. Stupid shit coming out of my mouth. I got it and I'm fucking playing it. You got nothing, man. Yeah, play your tech house. Yeah, I got this fucking complex out. Yeah, you stupid bitches. Hey, look at your little arms. You talk a lot of shit for someone with such a small truck. Yeah. Space between space and the research. Coming at you live. Coming at you live. Coming at you dead. Coming at you live. We are in the quantum space of the galactic. Reasoning for your plastic. Changing the space between. Yeah, you fucking atoms. Yeah, hydrogen, man. Swirling it, going at it. Bringing it, bring it up, bring it to sin, the motherfuckers. Yo, I'll play stupider shit than anyone else. Yeah. Las Vegas, give it up for nothing. SpaceyBlurr. Internet worldwide, coming at you from the nothing. Nth Dimension, quantum space between there, over and out and under, going at you from within, inside of your own self. But then we lost it. We lost it forever because I lost myself. I became everything, and then I was nothing, and then it's myself, and now I'm the one within the one in the universal cosmos way. Bring it back all the way to zero, all the way. 1, 0 is 0. Let's go beyond the 0. Let's go to the 0 beyond the 1. You remember? You remember the 0 beyond the 1? Do you remember? Do you remember the 0 beyond the 1? Let's make shittier music in this country. Let's make shittier music in this universe. Why doesn't anyone make techno like this anymore? I believe in the feedback loop. I believe in the feedback loop. Good night. I believe. Yeah, good night. Okay. I'm gonna stop the stream. Yeah. Let's fucking stop the stream. Thank you and good night. I talk to myself. Not just like when no one's looking, but I talk to myself in my live streams. I send messages to myself in the future. Like, I don't want to say I'm not crazy, but I might not be crazy. You know what? Fuck sleeping. You know what? Fuck you, man. Sleeping is the best thing I've ever done in my life, man. Oh shit. Yeah, I think my next music video, I'm just gonna find the spot in the clips of the Twitch. If someone wants to do it for me, that'd be cool, but I'm just gonna find a spot. I recorded something, actually. Blah. Yeah. I guess, I don't know. All I have to do is press the button. All I have to do is press the button remotely through another computer into another computer, and then it'll stop the stream. All I have to do. Wow, this is actually really good. Wow, you're so smart, me from the past. Hey man, I'm too underground to actually release an album. Listen to this man on Spotify. Yeah, listen to that man. Yo, coolios. I might actually I think I'm just gonna let it play out for a while. Thank you, I agree. I made a music video. I'll send you the link. Oh shit, I made a music video. I uploaded it to YouTube. It's like the complex modular systems out of a fractal mirror dimension. I'm feeling inspired. I'm just gonna let it play out. I'm using 2 low-pass gates, man. Oh my god, I am. I'm so fucking cool. Low-pass gates that much in my life, and now I'm just using them. It feels really good. Wow, dude, I'm so fucking cool. I'm using 2 low-pass gates and no filter. That's how fucking cool I am, apparently. It's a good sound design technique, but like you don't have to use that shit. But that was awesome. Like, that was fucking awesome.
Can be substituted into the Friedman equation and used with the scale factor instead of space. It can also be substituted to inflation theory and used with the inflaton scalar field.
Inflation, if you